Let's follow auto stop now out to the solenoid. And we'll start here again at our starting point, IC4 pin 10. And as we said earlier, this is normally low when everything is operating. So we have a low input to this NAND gate, and this output at pin 9 of IC4 is normally high with everything operating. That puts this NAND gate at the high input. It's connected as an inverter, so it's low. So pin 6 is tied to ground, and at that time these capacitors charge to the high output at pin 9 through this 1 megohm resistor. So we have positive on the bottom, the charge stored on those capacitors. Now also from this line, the high output goes down here to this transistor. Now, this is X6, and the high saturates the transistor, tying its collector to ground. So that puts the inputs to this Darlington pair at ground potential, and the solenoid is de-energized at that time. Now let's suppose auto stop is triggered somehow. Let's say we get a low at pin 11 of IC4, then we get a high at pin 10. Now we'd have all three inputs to this gate high. The output would drop low. And just following that out for a second, we'd have a low here and a high at the output of pin 6. Now we have that charge on these capacitors holding pin 8 high for a little bit. So that'll keep all three inputs high, but when those capacitors have lost their charge, pin 8 will drop, and then this gate will revert back to its normal state with the output high. So in the time taken for these capacitors to discharge, we'll have a low here. That's just a momentary low, and if we follow that down, that's going to cut off this transistor. Its collector voltage will rise, and now the base of the output transistors are returned through 5.6 k ohms and a diode to B+, and so we'd energize the solenoid momentarily. An extra action that's built into system control is X5, and that action is that when the unit is turned on with any of the keys except play depressed, the unit will automatically go into stop so that any function keys would be released. For example, if power were off and one of the keys were depressed, say fast forward, we'd have, when power is applied, 12 volts here on the operate line. That would go through this diode and this resistor directly to the base of the solenoid drive transistors and turn them on momentarily. However, in the play mode, we'd like to allow the machine to operate without triggering auto stop. For example, if you wanted to set the thing up to make a recording using the timer, then you'd have the keys in the play mode with power off, and when power is applied, you'd want it to go right into the play mode. So in this case, transistor X5, if we have the machine in the play mode, we'd have 12 volts at this point from the play key. This transistor would saturate and would ground this point. So this point would be returned to ground, and that entire action would be taken out of the circuit. So the machine could go right into play when power is applied. Now there's one more action we have to consider, and that is if automatic stop is triggered in the play or record mode, there still has to be power applied to the motors for unloading purposes. Now normally this transistor is off, and the motor control voltage goes out of system control to the servo system through D5. If auto stop is triggered, then this transistor will be turned on, and we ground this point. So now we've lost the source of motor control voltage. But there is another source. Let's trace this back a wee dab. Now here's the output to the servo, but we see an alternative source of voltage to the left up through R52. And now we have to follow the brown lead through this way and up, and we get to S7. Now, as long as the loading mechanism is away from the home position, this switch is closed, and this gives us our source of motor control voltage to unload tape. And the motor will continue to turn in this switch until this switch opens at the end of the unloading cycle, and then the motors will shut down. If something happens so that the motors continue to turn after the unthreading or unloading operation, it's likely that this switch did not open. Either its linkage to the loading mechanism is not proper, or the switch itself is defective. So that would be the place to look. We'd still have 12 volts here probably when we shouldn't at the end of the unload cycle. Now we're going to take a look at the servo circuits, and we'll look at the capstan servo first. That has to do with tape motion, errors in tape speed, and it's also a simple servo that works the same way in both playback and record. And in this servo system, this is the heart of where things come together. This is a sample and hold gate that compares two things. To the left, we have a trapezoid that's generated by a pair of pulse coils mounted on, or pulse coil rather, that is swept by a pair of magnets mounted on the capstan flywheel. And when the capstan is turning at precisely the right speed, the rep rate of those pulses is 5.29 per second, 5.29 hertz. Now, here we are comparing that signal with a frequency reference signal that comes from one of two sources depending on the machine. In the 3300, the source of the frequency reference is a tuning fork operating at 677.6 hertz. And that's a tuning fork oscillator followed by a Schmitt and by a divider circuit that divides by 128 and also produces 5.29 hertz. These two things are brought together at the sample and hold gate, and here we see the comparison. The output of this comparison circuit is a DC correction voltage that eventually gets through the discriminator, which detects very large changes in speed at startup, and through the motor drive amplifier to the capstan motor. So now let's go back, and we'll actually look on the oscilloscope at the phase comparison of the feedback and reference signals. Here's the waveform at test point 11. It's kind of hard to see because it's a very low frequency signal, 5.3 hertz. And there's two components that you have to look for. The voltage ramp, that descending sawtooth, is triggered by the pickup coils on the capstan flywheel. So if the ramp is missing, you have to troubleshoot back to the source at the pickup coils on the capstan flywheel, or opposite the capstan flywheel. The negative going pulse, about a third of the way down on the ramp, is the sampling pulse, and that comes from the frequency reference, which in the 3300 is the output of the tuning fork oscillator divided down by 180. But both of those things have to be there in order for the capstan servo to function. If both waveforms are there, but they are moving with respect to one another, not stationary with respect to one another as you see here, then there's some fault in the system between this phase comparator, between test point 11 and the motor drive amplifiers, the actual drive to the servo motors. So here's the place to start. You look for both of those signals. If either one is missing, go back through the appropriate circuitry to the source. If the sampling pulse is missing, that's that negative going pulse you saw in the previous shot, then go back to test point 13. That's the output of the tuning fork oscillator, actually the Schmitt trigger following the oscillator and the input to the countdown circuit. So this is the this input is at 677.6 hertz. If the sampling ramp at test point 11 is missing, and that's the sampling ramp is triggered by the output of the pulse coils on the capstan flywheel, then we look back at test point 10. And this is a very low amplitude signal. It should be 1/10 of a volt or bigger at test point 10, output from those pickup coils. The capstan servo in the 3600 is not quite as straightforward to troubleshoot because the timing comparison is made between the capstan pickup pulse and a counted down signal from a 358 crystal oscillator that's also counted down to 5.29 hertz. But the actual timing comparison takes place inside an IC, so we can only see what's going into the IC. And here is the ramp voltage that's generated by the capstan pickup pulse coil, and it's visible at test point 14. So that's one of the ingredients. The other is the other input ingredient you can only check at its source, the 358 oscillator, and that'll be at IC9 pin 3. Here's the signal at IC9 pin 3, and this has been counted down from 358 megahertz, and at this point it's 2,633.3 hertz. The drum servo on the 3300 has a similar servo system, and once again, for troubleshooting purposes, we start at the heart of the servo system where the timing comparison is made. And this is a sample and hold gate that compares two timing events. The ramp input to the trapezoidal ramp input to the gate comes via this route. A number of delay multivibrators, a flip-flop, two delay multivibrators, and ultimately the pickup coil mounted beneath the rotary head drum assembly, which signal the arrival of the reference head into the tape path. And we compare that event with a sampling pulse that comes from one of two sources. If we trace this back, we'll find that through this amplifier we'll have a source of signal from two routes. In the record mode, the sample is obtained from the video signal. Separated vertical sync is the reference for the servo system in the record mode. In the playback mode, the reference is control track signals that take this route through the control track amplifier and down to the sample and hold gate. So here again, we're comparing two things. The result of that comparison is a DC correction voltage, which goes through a discriminator which actually corrects for very large speed errors through the motor drive amplifier and then to the drum motor. Now we're going to take a look at the input to the sample and hold gate. Now here's that key test point at test point 7 where we bring together the sampling ramp that's triggered by head drum pickup pulses, and that pulse in the middle of the ramp and the machine in playback is the reference pulse derived from control track signals. Now if both of those signals are there but are moving with respect to one another, if those pulses are moving with respect to the ramp, then the fault lies after the sample and hold gate, between that point and the motor itself. If the ramp is missing, we have to trace back through to the pickup coils on the head drum assembly, and if the sampling pulse is missing, we have to trace back through its source. If the ramp were missing, then we trace back towards the head pickup coils. Here's test point 5. This is actually the head switching signal that's derived from the pickup coil signal, and that's what drives the trapezoid generator. If the signal at test point 5 is missing, we can go back to the source of signal at the pickup coils themselves. This is test point 4, and the signal at this point is 0.4 of a volt or more. Now if the sampling pulse were missing from the sample and hold gate, then we trace back to test point 3. And this is amplified control track pulses at test point 3. And the negative going part of that spike should be 0.6 of a volt or more. We can check the output of the servo system at IC5 pin 1. That's the input to the motor drive amplifier. And this is a DC voltage. We're using 5 volts per centimeter, and I'll go to ground on the scope. So this is about 10 volts. This is the DC voltage to the servo motor, and you can see the servo correcting. If you thumb the upper drum assembly while watching this point, you'll see that DC voltage change as the servo responds to the load. So that tells you that the servo is functioning. A faulty drum motor will fail to turn or will run erratically or only start if you give it a push by hand. And you can check for other failures by monitoring the voltage at test point 9, putting the machine in the play mode, and then depressing the pause key. Now, test point 9 is the invert input of IC 5. And we're going to measure this ripple. It should be less than a half a volt from peak to peak. And if it's from 1 to 2 volts, with 6 to 8 volts of DC at test point 9, then the drum motor should be replaced. The head drum servo in the 3600 is very similar to the 3300, except the test points are different. Here again, the key test point, that was test point 7 in the 3300, is where the sampling ramp and the reference signal come together, the sampling pulse. And here is, on the 3600, it's test point 10 instead of test point 7. And all the other test points are similarly changed. Troubleshooting the color processing circuit is largely a question of signal tracing. And let's start with the playback mode and trace the route of the color signal through the system. Now, the color playback signal at 629 kilohertz comes in by this route. Follows the amplifiers through an ACC block into a main frequency converter. Now here the 629 kilohertz signal meets a 4.2 megahertz signal that is derived in the APC-AFC network. We'll look at that in a minute, but let's suppose that the purple signal is there, and coming out here now we then have 358 in playback, and it follows this route through bandpass filter 2 and a couple of emitter followers, then through the comb filter, the 1H delay line that eliminates chroma crosstalk, and back by this route. Now, if I don't get lost, we go up through here through the killer amplifier, which turns off chroma if there's no burst in the signal, out of the killer amplifier. Now the color signal is finally corrected at this point, and it meets the luminance playback signal in this mixer amplifier to form the composite output signal. Now in playback, the change from 629 kilohertz to 3.58 megahertz took place at this converter, and it can only take place if we have 4.2 megahertz input. So let's follow this down and see where it comes from. Out of pin 5 of IC8, and we'll go back down through a bandpass filter to IC14, pin 8. Now, here's a subconverter now. This converter is mixing two signals, 629 kilohertz from an AFC, automatic frequency control loop, and 358 megahertz from an APC, automatic phase control loop. And the sum of those two signals is selected by this bandpass filter to be 4.2 megahertz. Now, if we don't have 4.2 megahertz out of this filter, we have to follow the two inputs to this subconverter. And we'll start now with the AFC loop. The AFC loop works on horizontal sync. So playback horizontal sync comes in at this point, and we're going to check for jitter and frequency error in horizontal sync. And we come down through these two inverters, and over in this direction, through a multivibrator that determines the duty cycle and pulse width of that 15734 kilohertz signal into a phase detector. Now this phase detector is going to phase compare horizontal sync with a signal from a VCO at the same frequency. So let's go back to the VCO and see where it starts. Now this is a voltage controlled oscillator that runs at 160 times the H rate. And the output is at pin 8. You can find it at test point 16. If we follow that route, we'll go into a divider. Now this divider divides that H rate signal first by 16. We come out at pin 6, 16 times into 160 times 15,750. Then we divide by 10, and now we have an H rate signal coming out at pin 11. So we have two H rate signals being compared in this phase detector, and we get a DC output proportional to frequency error. And that DC output is used to control that voltage-controlled oscillator that runs at 160 times the H rate. Now when that oscillator runs at the correct frequency, we put it into the divider once again at the same place, and we take outputs at various factors, various division factors, and they are selected by this data select unit to provide as a final output to the sub-converter a 629 kilohertz signal which steps 90 degrees in phase at the proper directions at the line rate. Now we have one input to that sub-converter. Now let's follow the other one. That's from the APC loop, which corrects residual phase errors not taken care of by the AFC loop. And we'll go back here to a voltage-controlled crystal oscillator that runs at a center of 358 megahertz, but it's phase corrected by a DC voltage coming out of this phase detector. And this phase detector compares two things. One of the inputs is a reference input from a reference 3.58 megahertz crystal oscillator that's independent of everything else. The other input to the phase detector is burst, separated from the actual playback signal. So this is the final correction. We correct playback burst against a reference crystal oscillator. Playback burst is also used to operate the color killer. Here a sample of the burst signal is fed to this phase detector, which also gets a feed from the reference oscillator that's been shifted 90 degrees. Now if the APC system is locked up, that means that burst and that shifted signal will be in phase in this phase detector, and we'll get a maximum DC output. And this DC output is fed to this op amp and forms the DC output that allows this killer amp to pass signals so that if there is burst in the signal, the chroma signal will be processed. Let's follow the reasoning behind troubleshooting a no color in playback situation where color is okay in E to E. The first step is to check for 5 volts at pin 2 of IC11. That's a regulator on the YC board. Should be 5 volts. If not, check IC11 or its 9-volt input. If you have 5 volts, then go to test point 20 and see if there's horizontal sync input. Now, horizontal sync should be visible at test point 20. That's necessary for the AFC system. If it's not there, check transistors X26 and 27. And if there's no horizontal sync at this point, go back to the audio and servo board where sync initially comes from. Now we're going to start at the root of 629 kilohertz playback signals at test point 7. The signal should be about 0.4 of a volt or more when playing back standard color bars from the alignment tape. If it's not here, check the preamp board, IC3 and 4, and low-pass filter 1. If they are there, we proceed to test point 10. Now, if we have signal at test point 7, then we can go to a next test point along the signal path at test point 10. Now, if we have no signal at test point 10, then we could have a break in this feed line, the 1H delay line, these emitter followers, bandpass filter 2, or the frequency converter in IC8. And for that frequency converter to work, we have to have an input from the sub converter. Well, let's assume that we do have an output at test point 10. We do have an output from the subconverter then, and we'll follow that signal route around to test point 8. Now test point 10 should be about 0.8 of a volt peak to peak. Test point 8 should be about 0.3 of a volt peak to peak. Now when looking at test point 8, there's something you can do that will help to localize the signal. Look for color while you ground pin 2 of IC10. That will enable this killer amplifier, disable the color killer, and enable signals to pass. Now if you still have no color, then you have a failure of the AFC APC input to the converter, the main converter. But now if you see under those conditions, if you see color noise, then it's probably a failure of the AFC loop, and we'll do that separately. If you see horizontal color stripes in the color bars at that time, then it's probably a failure in the APC loop, and we'll look at that separately. If we still get no sign of color with pin 2 of IC10 grounded, then check to make sure pin 6 is high, 11 volts with pin 2 grounded. And if it is, then the color killer should be disabled and we should get something through there. And if we don't, then IC8 should be replaced. If 6 is high, 11 volts, and there's no color noise or anything visible, then IC8 probably needs to be replaced. Now suppose our previous check gave us the color noise when we grounded pin 2 of IC10, and it indicates a failure of the AFC loop. Now we'll troubleshoot it. First thing we look at is test point 17, and we should have an H-rate signal with about this duty cycle. We showed you earlier in the tape how to adjust that duty cycle, but we should have that signal about 12 volts peak to peak at test point 17. That's the horizontal sync input to the AFC net. Next we go to test point 16, and this is the signal that's 160 times the H rate that comes from the voltage control oscillator. Next we move to test point 12. This signal is 1/2 of F sub H. And if we had the previous waveform and we don't have this one, then we have to check or possibly replace IC18 or IC12. If we do have this signal, then we'll proceed to both pins 1 and 2 of IC12. Now if we have that signal at test point 12, we look at pins 1 and 2 of IC12. We'll see the same square wave. And if we don't have the signal, this signal at pins 1 and 2, then the flip-flop in IC12 is probably defective. If we do have it, then we'll go to pins 12 and 13 of IC13. This is the drum flip-flop input. It's the head switching signal input to the system. And if we don't have it, we should check the drum flip-flop input at test 21 or the inverter X20 and IC16. We should have these square waves of opposite polarity at pins 12 and 13. Now if we have those signals, then we're going to look for a signal at pin 7 of IC14. And if there's nothing there, then the data selector IC13 should probably be replaced. And if we do have a signal at pin 7 of IC14, then we should look for signal at test point 14. Here's the signal at test point 14. That's the output of the subconverter. And we've already traced out the AFC input. Now if we don't have a signal at test point 14, it's probably the APC input that's missing, and we'll check that out now. We'll start our check of the APC loop at test point 13. This is the 358 reference oscillator, and we should have a signal here about 1.8 volts peak to peak, 358 megahertz. If it's not there, check the crystal and transistor X19. If it is there, we'll go to test point 11. Test point 11 is the output of the burst gate, and we should have about 1.5 volts peak to peak of burst at this point. If there's no burst, then we should check for horizontal sync at test point 20, and if it's there, then the burst gate is probably defective. The burst gate is 18. If there's no horizontal sink at test point 20, then we should check transistors X26 and 27. Well, let's suppose we have burst at this point, and then we'll progress to test point 15. Here at test point 15, we have about 3.5 volts peak to peak. This is the output of the voltage-controlled crystal oscillator. If there's no signal at this point, then check the 3.58 crystal in the VXO and IC15. Now we move the probe once more to test point 14, the output of the subconverter. Now we've checked the AFC input and we've checked the APC input. That was test point 15 that we just checked. Now if we have inputs at both of these points and no output at test point 14, then IC14 is suspect and bandpass filter 3 should be checked. In other words, check for an output at pin 8 of IC14. If you have it there and not at test point 14, obviously this filter is defective. And that completes the playback color troubleshooting system. Well, we hope you found this training tape informative and interesting, and we hope that it will help you to get a little bit more speed on the bench.